Was that you? I thought that was in the hallway.
And so we have a quiz Thursday on campus. So is it about stuff that we've already learned, or is it about this?
No, it's about it's a recap of everything you learned in resistance-only circuits.
Okay.
And you can open the quizzes and then work on them and then close them and then come back to them later.
We can?
You can.
Oh. I didn't know. I found it up. I thought you had to leave the tab open.
No, should give you a little bit of assistance. I do that with all my quizzes because then it's less of a quiz and more like a homework assignment.
Yeah.
I should just call them homework assignments, but I'll probably do that next year.
And so you press take the quiz.
Yeah! Okay, and there was one thing that I wanted to say to all of you. I had some questions about the quizzes. Your quizzes are not worth a whole lot of your total grade. That is intentional. Your quizzes serve as exceptional study material to get you ready for the exam. Because there's more than one of them. So if you do poorly on the quizzes, it benefits you to go back and try to figure out what you did wrong. Okay? So that when it comes time for the exam, you should be ready. Some teachers will give you the same, like, you did this question already, just do it again on the exam. We're not doing that, okay? There are different questions that will be on your exam that have not been on any of your quizzes. We will have to address those. But if you understand the concepts of what you did in the quizzes, none of the questions on the exam will be any different. Okay. So we've got this relationship between current and voltage in an inductor. Now I'm going to go ahead and just draw a simple inductor system. So here, this is a current source. This is your inductor, okay? According to KVL, we know that all of the voltage provided by the source is equal to all of the current provided, well, all of the voltage that's consumed by your inductor. Because of this relationship, if IS is constant, what that means is that Vs is equal to 0, because that's also equal to VL. Which means we have a current source where current is flowing through the system, but there is no power being supplied to the system because there's nothing to consume it. In a constant current system, there is some power that has to be put into this component in order to generate a magnetic field. That happens nearly instantaneously at the speed of light, where suddenly the energy level just jumps up, okay? It's not realistic, it actually takes time for it to charge. But in a perfect component, we assume that it just jumps, and then all of a sudden it's just, bam, there's magnetic field, okay? So walking through the same exact type of thing that we just did in the last class, waiting for my Russian comments. Come on, come on. Daddy wants another link. Dang it, that got on YouTube. Frag. I need to be careful about what I say. When it comes to inductances in series, okay, when you place an inductor in series, here I'm taking another current source, and we'll take 3 inductors in series, okay? L1, L2, L3. By KVL, we know that Vs, and this is Is. Vs is equal to VL1 plus VL2 plus VL3. By KCL, we know that Is is equal to IL1, that's not a 1, is equal to IL2 is equal to IL3, okay? KVL and KCl give us a very simple way of looking at this. We know that all of our voltages are going to sum to each other, and we know that all of the currents will be the same. Doesn't matter if the current source is changing, doesn't matter what's going on there. It has to sum to this, okay? Ooh. You guys are terrible. That's right. Duncan, you shouldn't be exposing yourself on YouTube.
Oh. But I am not.
Right. Sorry. My apologies. Okay. So if we look at this, because all three of these have the same current, when we plug them in together, since they all have the exact same current, if we just continue to add more inductors, it's going to add more energy to the system. Believe it or not. Which means that inductances will end up summing the same way as resistances do. Okay, and again, the book proves this, and I don't want to take the time to do it. When we talk about equivalent inductance in series, L equivalent is equal to L1 plus L2 plus L3 plus ... It's the same kind of relationship we saw for resistors. Okay? Exact same. And if you want to use this equation, I mean, you can. This doesn't have the nice, neat charge equation that the capacitors have, so we're not really breaking it down into charge. It does have a nice energy equation, but we'll get into energy equations right after this. So when we also then go talk about parallel inductances, so here I draw my current source. Here's 1, here's 2, here's 3, IS, L1, L2, L3. Because of the current division principle, there is going to be less current that ends up traveling through each of those inductors, which means the total inductance of this system actually ends up being less than what the original inductance system is. Now here we can again talk about by KVL, Vs is equal to VL1 is equal to VL2 is equal to VL3. And by KCl, Is is equal to IL1 plus IL2 plus IL3. Okay. The equivalent inductance in parallel is given by 1 over LEQ is equal to 1 over L1 plus 1 over L2 plus ... Okay? So it's exactly the same as what we saw for equivalent resistance in parallel. Capacitance is the opposite. It's actually equivalent to conductance. I never mentioned conductance in class, but the book mentioned it, and you had to do it for your reading assignment. The equations for conductance are the same as the equations for capacitance. The equations for resistance are the same as the equations for inductance here. If you really want to think about it like that, we don't really deal with a lot of conductance equations because it just doesn't make nearly as much sense as resistance equations. But that relationship does exist. So we can continue on with this idea. None of this is too terribly shocking. We'll do an example problem towards the end of class where we calculate equivalent inductance and equivalent capacitance. This is kind of dumb. This is, if you understood the concepts from chapter 2, this should be a cakewalk for now. The component equations, that is the VL is equal to L DIL dt. That is going to come back to bite us next chapter. I'm actually, yeah, I don't know if, oh, yeah, I've got a couple things to mention on that. But yeah, we're not really going to play around with that a whole lot right now. All right, so just like we saw in the discussion on capacitors, there is something called a practical inductor. A real inductor this experiences okay, real inductors do generate heat. Inductors are just giant wires. That's awesome. But because of the flow of electricity and because what you end up with is there is some element of magnetic resistance that is created by an inductor in a real setting, it ends up actually causing currents in other items that are around the inductor, which causes a separation of charges, which ends up actually creating an electric field in a very small amount. Okay, so the model of a real inductor is you have a resistor, this is called RS, and then you have CP, L, and RP. Okay, let's talk about what each one of these components represents. So here, RS is the amount of resistance of the wire that the inductor is made out of. Okay? We can reduce RS by actually turning these components into superconductors. It's kind of an interesting thing to talk about. Superconductors are basically when you super cool some electrically conductive materials, they carry charges in a very different way that causes their resistance to be near zero. But something fun to talk about. CP is the electric field that's generated by forcing current movement in other objects. Or I'm going to call it forced charge imbalance. Okay, and then RP, what this represents is it's actually the amount of current that is, it's kind of like an eddy current, which is what we saw in the capacitors. But basically the whole goal of this is there is some amount of rotation inside of it that goes and defeats the magnetic field, so it lowers the magnetic field. And ultimately all of that energy just ends up as heat. So that's what each of those components mean. The book doesn't really explain those, but it's just a fun thing to think about. Again, we're not going to be using real inductors here. We're going to assume that the resistance of these wires is zero. We're going to assume that there are no eddy currents that reduces the magnetism. We're just going to assume all of these things because it makes the calculations simpler. Okay? You have a question? You having a hard time reading what I wrote? Generated?
The last word.
Oh, imbalance. This is forced charge imbalance. Imbalance. That's an M. Okay, so any question over this model? This is a super boring lecture. Just wait till it gets super hard. Okay, seeing none, motion passes.
You said it should be a cakewalk. It doesn't actually make it easy, it just makes it appear
It appears easy, and in this context, we're not asking a lot out of you.
grace and elegance.
Yes, it's mostly the flowy diagrams. Right.
Dance, the phrase cake.
Well, let us move on. Now, what we are going to discuss is energy. I'm going to find the equations to make sure that I tell them to you correctly, because that's kind of important. Wow, this marker is just slowly losing its life.
Oh.
It's right next to the other marker I threw there and never picked up. Oops. My bad. I'm gonna go grab a new marker. All right.
She was grumpy about that. She said Kvl and Kcl. Well, we did this together in class. I guess she did class. No, okay, I did not understand it. I don't think.
All right, so let's talk about energy. Okay, so as I mentioned, the energy in a capacitance is stored in an electric field, okay? Now the equations for electric field energy are not kind, but we can simplify them to just look at how it behaves in our circuit, and the way we treat it is that energy as a function of time is equal to 1/2 C V squared, where V is a function of time, okay? Now do note here that we can use our relationship between V and Q to identify another energy equation, both of which are given in your book, both of which I suggest you write down as a part of your equation sheet because they are important equations. This is only true for capacitance, again, because it has a capacitance in it. If you have a component that doesn't have a capacitance, it's not going to abide by this equation, okay? The idea here is the more voltage you have on a component, the more energy you're going to have. Okay, but similarly, because of Q equals CV, the more charges are separated on plates, the more energy you will have. Okay, so that's kind of two big important pieces here. Now, if we were to study the power consumption that's provided to a capacitor, we always know that the relationship P equals VI is true. It is always true. It is never not true. It fails the ability to be untrue. Okay? How many double negatives can I get? It fails to lack the ability to not be untrue. There we go. I could probably keep going.
That's for capacitors and resistors.
This is true for all components. This is electric component power. This is true forever. This is true for inductors. It's true for anything. Now, specifically for capacitors, well, and this is also true. This is also equal to the time derivative of energy. That's also true for everything. But capacitors have a very specific energy relationship here. Okay? So what you can do is you can take the time derivative of this equation, the power as a function of time is equal to 1/2 c times the derivative of v of t squared. Okay? If v of t is constant, you have no power being consumed by the device, quite frankly. Which you can also see by looking at this, because if v is constant, you have no current. So kind of same, it's two different ways of looking at the same problem. But you still have energy that's present in your capacitor. Unlike a resistor, this only depends on whether or not there is a voltage. If there is a voltage, there is energy. If there is no voltage, there is no energy. If you ever disassemble an electric circuit on your own, you always have to discharge the capacitors. Okay? I don't care how much you trust those manufacturers. You touch a capacitor, it will shock you and it hurts. Okay? It's not fun. And that's because there is energy storage and there doesn't have to be any movement in the system to do it. It's just a static component. Everything is standing still, storing energy. And there's an electric field that's present. The moment you touch those two terminals together, you complete the circuit, you shock yourself. That's actually how a taser works. Yeah. Probably not, because an electric fence uses capacitors. And actually what it does is it charges the capacitor, discharges it, so it's not like constant electric current. It charges it, quickly shocks you, and so it like spreads it out over time. It causes it to hurt more. It's fun. Have you ever peed on one? Peed on an electric fence? I never had the motivation to.
Yeah, I think I'd rather stay safe.
It's nice that you value your future children.
Yeah. But it's so.
It would.
It does.
Wait, it does?
Yes, it does. And you're grounded because you're touching the ground. So when you pee on an electric fence, it shocks you. It shocks you in places where the sun don't shine.
So if you're side is why
Huh?
you can float in the air, like, you know, it's like
You would get a small amount of shock because your body then acts as a capacitor and you store excess charge.
Nice. So I charge myself for
so like you turn into
So if my
Yes.
in my pocket,
All right. So,
I'm about to.
so basically, if you pee on an electric fence, if you're in the Marvel universe, you turn into Thor. If you're in DC universe, you turn into Flash.
only if like what was it, the dark matter.
And if you're in one of those other like weird comic creators that are very obscure,
Oh, what about the
you just die.
Electro? You can also you might turn into Electro as well.
Oh, that's true. That's true. I forgot about that. Yeah.
Is it gonna be on the quiz?
All right. Yep. No, that's gone. Worst part is this is on YouTube, so whatever. Anyways, oh dang, it is in the view. Drat. So this is all true for capacitance. If we then turn around and look at inductance, how do we get on the topic of being an electric fence? You had the question, and I just took it that next level. That's right. You know, it's a wonder that humans as a species hasn't died out.
Hey, we've gone through a lot today.
Well, there's 8 billion people or something like that on the planet, and only about 20,000 run it, so.
That's true.
That's because we're like rodents, and as soon as we're doing dumb stuff to kill us, we're also just recreating like 8 of us.
That's also true. Yeah. It's all because Skylar decided to preserve his future children. Dang it, Skylar.
It's all because I didn't want to pee on the fence.
Just friggin' pee on the fence. Yeah, that's how we know we're in the DC universe. Okay, so when it comes to inductors, inductors store energy according to the equation 1/2 Li of T squared. Well, it's a half lit.
Oh, it's lit squared.
Half lit squared.
Brings it to normal.
Just makes it, yeah. You got 2 2's in there, it just forms a 1. All right, so induct, huh?
As a function of time.
Yes, it is. Because the idea here is that your total energy takes into account the amount of current that's present in it at a specific time. This is not cumulative according to energy. It is cumulative according to voltage. It's net sum of voltage over a certain amount of time generates this, but here this is instantaneous for current. And we could say the same thing for capacitance. It is instantaneously dependent on the voltage, but it is cumulatively dependent on the current. You have to do an integral of the current. All right, so a couple of implications from this. Again, more current, more energy. If you have any current flowing through an inductor at all, there is energy stored in that inductor. Now there is some benefit to that because it means you can turn on and off the energy traveling through an inductor, and the energy that is being stored then has to be released. Which means you can power a circuit incrementally, and this is true for both capacitors and inductors. You can incrementally power it, and it will spread out the power by having your inductors and your capacitors charge and discharge. Okay? Going back to the charge-discharge circuit we drew earlier. Okay. It does not require a voltage for there to be energy inside of a capacitor. All it requires is for there to be a current flowing. That said capacitor, I meant inductor. Now, once again, your power equations over here are still true for inductors. If you want to know the instantaneous power consumption, you have to calculate 1/2 L times the time derivative of the current squared. Okay, this is again instantaneous. This is not something that is cumulative. It does not depend, it does not have a prior time dependency. It only focuses on the exact moment when this is happening. Okay? All right, any questions on these? Again, this is pretty bland. This is not super exciting. Oh, oh.
Okay, it's fine.
I can rewrite it. Do you want me to rewrite it?
Yeah.
My bad. I should have started on the stuff that, you know. I just get really excited and just want to move on. What? Yeah, he doesn't like me anymore. That whole thing about where we're talking about electric fences, it's disturbing on an emotional level. It's just too much. I came to class to learn, not to be emotionally scarred.
You know what I learned today? That if you pee on an electric fence, you might get in trouble.
You might gain superpowers. I would tell that to a college student just to make you do it. But then if you die, then I'm going to be like, oh, oops. He totally took that out of context. Don't do it, okay? That whole you might die thing, it is real.
Don't get lost in the
I don't know where an electric fence is, so I'll probably say no.
Let's keep it that way.
Alright, we're gonna make an electric fence.
In class, and then I'm going to turn around.
And then one of us is going to say,
Design project is become a superhero.
yes.
All right, let's do an example problem real quick. We'll do 2 of them. Should be able to do it. Knock it out. Mostly what this chapter is it's preparing you for the next chapter by talking about the fundamentals of what are these components? Why do they exist? What's so special about them? And the next chapter, it's how do we do calculations with them? And then it's like, ah! And then that's when things really hit the fan. So next week, things start getting more fun. Huh?
I just look up, whenever you use a cliche expression, I look up where it came from.
Things hit the fan? I don't want...
Cakewalk came from like a 1870s plantation dance. That was a competition for cake.
That sounds awful. I don't think I can ever use that one again.
Cakewalk.
That's horrible.
Well, it was actually like the plantation owners like encouraged them to be really extravagant. But like people believed that they just didn't understand that the slaves were mocking them. And so the winner was whoever mocked the owner the best.
That's funny. That's actually kind of clever. Okay, I'm not ever gonna not use that again.
Oh, some sources suggest Canada is to blame for hitting the fan.
Well, it does sound like a very Canada thing. All right, we'll do an example. So, all right. And oh, I never said that the unit of inductance is henries. Usually, when you're talking about inductances, you're talking about a range of anywhere from 0.1 to maybe 100. 100 is a huge inductor, but this is still what we're dealing with. So the question is, what does, not V, what does the graph of energy through this system look like? Okay, so now here the voltage source is constant. There's a constant DC source. It's a very simple system. What does this look like? Okay, so when I ask for something like this, we know we have our equation that I just erased from the board, which is 1/2 Li of t squared. Here, we have a voltage source, not a current source. So we know that KVL is true. So I'm gonna go ahead and circle that one. That'll be equation number 1. It's our energy equation. We got KVL equation, which says that Vs is equal to VL. We'll call that equation number 2. We have our KCl equation, which says that Is is equal to IL. That can be equation number 3. And then we have our component equation, which is VL is equal to L DIL dt. Okay, Okay, and I'm going to go ahead and call that number 4. We have 4 different equations we can use here. Okay, you have your constitutive equations, you have your component equation, and then you just have your energy equation. All right? Have I lost anybody yet? Dang it, I'm not doing it. I'm trying hard enough. Need to build 2 electric fences. There we go. Or I'm just gonna dress up like John Cena.
I was literally about to say something.
Got you, fam.
Where that came from.
Why don't you look that up? Do you know?
I watched a video, I forgot though.
It's from his brother or something.
Like they talk smack like championship.
Yeah, his brother told him like you won't say it or something like that. He said it
Oh,
in
his
every-
brother said something about him, like, getting his butt beat or something, but he was too fast or whatever, so he said he kind of, like, he wouldn't see him coming because he was too quick. So that's where that came from. But
Interesting.
it was just this, but then, you know, that wasn't cool, so he
Got it.
This was cool, so we did this. Yeah, because imagine if you just ran out like this.
Yeah. Ah, fear me. And everyone's like, I can see you. Like, oh, wait. No, I can't see him anymore. It's gone. Okay, so we have these 4 equations. Now, here's the equation we're aiming for, because that's what's going to give us what we want. So we need to solve this in terms of I. Okay, we don't know IS. We do know VS. So I'm going to go ahead and take this one. VS is equal to VL. I'm going to go ahead and I'm not going to use this equation because it doesn't help us. But I'm going to jump into this one, and now we can say VS is equal to L DIL dt. Okay? So then we can rearrange that, solve for I. DIL dt is equal to VS divided by L. We take the integral of both sides, and we have IL is equal to the integral of VS over L. dt. I just took an integral of the derivative. So if I want to break this step out, technically it becomes DIL is equal to VS over L dt. And then you just integrate both sides. And then when you integrate 1 DIL is equal to VS over L dt, you end up with DIL, which just ends up as IL.
Oh, so it's not E times L, it's Y or I L.
Yeah, I subscript L. It's the current specifically in the inductor. Since we know VS is equal to 5 and we know L is equal to 1, we can go ahead and solve this out because this is equal to VS over L times T. We can assume that at time 0, that the current through the inductor is equal to 0, which means C is equal to 0. Okay? But otherwise, because you have to do that in any time you do your integrals, we can't just throw that away. It does depend on the initial condition here. Because it is cumulative. This is one of the cumulative relationships. Okay, so IL is equal to 5 over 2 times T. Whoa, 5 over L, that's right, 5 over 1. Which is just equal to 5T. That's not too bad. Yeah, we make it lit. Yeet. So the equation that we end up with is, because this is a function of time, we can make this be a function of time as well. W is equal to 1/2 times 1 times 5t squared, which means that W is equal to 12.5 t squared. Anybody see what the problem is with this? Let's graph WT versus time. The longer this is plugged in, the more energy it stores. This is extremely dangerous. In fact, you reach a limit to the amount of energy that can be output by the power source very quickly. Sometimes that happens by the power source actually exploding. But overall, this is very dangerous. Okay? This is a bad day. This is why every time I presented an inductor to you, I had to have a current source and not a voltage source. This is why.
I exploded something in my high school engineering classes.
It's possible.
I put it straight to a battery and I had it wrapped around a nail. And then, yeah.
Yeah, that would do it.
So to make sure we understand this concept, when we all explode some voltage sources.
No. All of a sudden, the fee for this course is going to be like $500 just to take this class so that we can blow stuff up?
I would pay $500 for that.
You don't have $500.
You're not wrong, but that was your job.
I spend my weekends begging in the streets so that I can blow things up.
Aren't we supposed to learn from our mistakes?
Take out a bank for it.
Well, how about you just learn from the theoretical mistakes you could be making, such as electric line. Okay? All right, so the same principle is true if we were to take a current source and plug it into a capacitor. Because again, if you're forcing a current to happen, the big issue here comes down to this relationship. If we force a voltage requires there be a change in current. So if you force a voltage to occur across this component, it requires a change in the current flowing through that component. The same thing goes with a capacitor. Here, IC is equal to C dVc dt. If you force a current to travel through here, it will cause an increase in the amount of voltage across here. This is actually an interesting concept. Have any of you seen the Van de Graaff machines that generate like 20,000 volts? Yeah. This is how they do it. You just have a giant capacitor and you force current to flow into it. That's all it is. Which those you can build. They can be dangerous if you build it right. Most people don't build it right. Losers. Lames. Some people just don't have that drive. But this is really what it comes down to. This is why this is a problem. This is why this is a problem. Okay? So do keep in mind that this relationship does occur. Now we're going to do one quick example of equivalent capacitance, and then we'll just be done. You'll have a quiz due next week that's on equivalent capacitance and equivalent inductance, talks about some capacitance and inductance properties. You know, fun stuff. All right, so let's say I'm just going to take two terminals. I'm not going to apply a power source. But what I'll do is I'll have a capacitor, then I'll have a capacitor, capacitor. I'll have it go into a capacitor, and then separate into a capacitor and a capacitor. Okay? Thanks, bro.
Can we add one more?
You are now
Sure, we can throw one over here.
Yeah.
Okay, so this will be C1, C2, C3, C4, C5, C6, C7. This one is the one you gotta worry about. That one blows up. Well, it's C4.
Oh.
That was good.
That was good.
All right, so the way that we would combine these is we would say, okay, let's combine the ones that are in parallel first. So we have C1, we'll call this CEQ1, CE4, and then we'll call this CEQ2, and then C7. Okay, and here, because we're combining them in parallel, CEQ1 is equal to C2 plus C3, and CEQ2 is equal to C5 plus C6. Then we combine them all in series to form just one, CEQ3, where here 1 over CEQ3 is equal to 1 over C1 plus 1 over CEQ2, 1 plus 1 over C4 plus 1 over CEQ2 plus 1 over C7, okay? It's exactly the same way as we would have done an equivalent resistance circuit. It's just this time, we're not using resistance. Now the same principles apply here. The amount of current that is flowing through this component is equal to the amount of current that's flowing through all of these series components. That stays true from the equivalent resistance circuits. Similarly, the amount of voltage across this component is equal to the amount of voltage between these two nodes, which is equal to the amount of voltage across both of those components. So when you expand in parallel, voltages are the same. You expand in series, currents are the same. Okay? Any questions? All right, get out of here. Go enjoy your lives. Dang it. No. You get out of here and you get out of here early. I know you.
You should say that like 2 hours.
What?